Okay, so welcome. I'm Chris Benson. I'll tell you a little bit about myself. This is Artificial Intelligence Strategy Delivering Deep Learning. It's the first in a series of AI strategy talks I'm going to be putting together, and one that I've started doing fairly regularly, although the slide deck is different every time. So as you'll see me kind of glancing to figure out where we are, because I get to the end of each talk, and for the next one I like shuffle everything around. So it keeps me on track. So my name's Chris Benson. I work for Honeywell, a particular division within Honeywell, or what we call a strategic business group, which is called Safety and Productivity Solutions. It's one of 4 of the global divisions within Honeywell. And I'm responsible for everything AI, ML, DL, data science, you name it. So we are obviously a gigantic manufacturing company. I think we're 73 on the global Fortune 500. So it's a big organization. And before that, I was at Accenture for a fairly short amount of time before going to Honeywell as an artificial intelligence delivery manager. So what those basically mean is my job is to actually make the stuff happen. And so it's one thing, I love talking about it and everything, but when I actually go in the office, we're down to the wire and doing stuff. So I do a lot of AI and machine learning strategy. This is the first day that I've been at the conference, because I've been out of town with an AI team that I have in Pittsburgh that specializes in speech recognition. How's the conference been so far, by the way, since I haven't been here until just now? Has it been pretty good? So this is fantastic. The organizers are friends of mine, and I love this one because it actually pulled from the community. Everybody could apply to speak to it. And not all data conferences are like that. Some of them, they kind of decide who's going to speak, and without any input from the community. So I love seeing everybody supporting this one. Do a lot of hands-on deep learning architecture, and I'll talk a little bit about that in detail as we go forward. Does anybody here attend the Atlanta Deep Learning Meetup by chance? There's a few faces. There we go around, and that is, we started it at the beginning of this year, and it has become, as far as I can tell, the single biggest AI community that's active in the world at this point. I've been looking around trying to find others that are more social, not necessarily a university, that kind of thing. And we have I think 1,300 people that are in it, and we typically have 60 to 80 people come in per month. This last one was about 80. And that's just month after month. So you're welcome to come. It's a block from here at ATDC on the 2nd floor. We are skipping December, but we'll be back into it in January. So I invite you to come. A lot of public speaking on this stuff, and I'm about to talk about it, but I actually got introduced to deep learning way before it was called deep learning, about 25 years ago. And I spend a lot of time talking about, and in my job, working on the future of what deep learning will be and what it means to a large corporation like us. I flew in from Pittsburgh last night, like I mentioned, and on the drive home from the airport, my CTO calls me up, and I'm like, oh no, this is not good when he calls you at 8 o'clock at night, and I'm like, hi, and he said, I have an assignment for you. And so we brainstormed for the next 5 hours until a little after midnight last night on where we're putting millions of dollars. And I just want to say, boss, I'm really not ready to do this because we got talks tomorrow and stuff like that. So, but it's moving so fast that the company is pivoting constantly. It feels like being in a startup world, which is kind of where I've come from before these last 2 big companies. Been programming since I was 11. Started out on that. Anybody recognize that? Oh, yeah. Mm-hmm. So the original IBM PC. So I'm one of those rare people at my age who had parents that were already doing this stuff, and actually were doing the earlier versions of AI and such, and I'll talk about that. This is what I work with now. Anybody know what that is? That's a DGX-1. It's the world's fastest AI-specific supercomputer, and that's what we use at Honeywell. It's also what Facebook uses, a lot of the big AI departments. So I mentioned, introduced to deep learning about 25 years ago. This was built here in Marietta, Georgia, just a few minutes north of here, the Lockheed plant. And they had an interesting situation arise in April of '92. They had an avionics failure. Let me see if I can show this. It doesn't have sound. Oh, I've just gone ahead. There we go. And they were doing test stuff at Edwards, and whack. The pilot was trying intentionally, the test pilot, to crash the plane, And the avionics were supposed to prevent it from doing that. And so it goes skidding down the runway. I'm not sure it's actually showing, I guess it's done, for quite a long ways. And that was a big problem for the Air Force. It was a big problem for Lockheed. And to this day, this is still the top air-to-air superiority fighter, even though we're 25 years later. So they basically turned to this guy. And he was an engineer, really focused on the bleeding edge of stuff. And neural networks of the day, which was a whole different world from what we're at right now, he applied that. And he ultimately, after about a year, was able to solve the problem. It's my dad, and that's how I got introduced. So I was a college kid, and I used to come home, and he'd come home every night, and this was our dinner table talk. How he used neural networks, starting with backpropagation, then moving to other algorithms to solve this problem back in '92 and the beginning of '93. So then I went away from this stuff after I got a real passion for it, went away, and then, hey, look what's happened with deep learning these last few years. So I've swung back into it. So before I leap into this is going to depend on how much depth or how much I don't go, how much I fly over it. Raise your hands if you're pretty familiar with deep learning, if you think you understand how it works and everything. Because if there's only a few hands, I'm going to take a few minutes to kind of give you an introduction into it. And if there's not, so I saw probably 10 hands. So I'm going to take a little time. And if you already know this stuff, you can just take a nap, and that's no problem. But it's hard to talk about delivering deep learning if you don't have a sense of what deep learning is and what kind of things it's trying to solve. So I'm going to run through that for a few minutes and talk about why it matters. So it is the modern version of AI that works today, is what I tell people. That's a very pragmatic way of looking at it. It's an approach to deep learning that is driving the current AI revolution. Everything you are seeing on CNN, all the mainstream media, we're not talking tech media even, just mainstream media, this is driven by deep learning. For all practical purposes, I would say that deep learning is AI. There are other things in machine learning that are not deep learning that are still widely used, but deep learning is kind of the big daddy of them, and there's really no major applications you're seeing out there that are sufficient enough to be on the news that are not being driven by this technology. So it's an approach to machine learning that basically is trying to mimic what we do in the human brain. It's not exact. It's a really loose, rough idea, but a lot of the research will say, well, how does the visual cortex work when we're doing machine vision, things like that? And the researchers tend to follow those lines and see if they can come up with something. And so, did I get to the next one? Yeah. So the idea here is that you're trying to learn from experience. And so you're learning from data without explicit programming. Now, I'm actually not a data scientist by background. I'm a software engineer by background. And I have spent the last 25 years writing code, which essentially in various languages had either if-thens or cases or whatever, all these statements. And we sit there for a huge amount of time trying everything we can possibly do to figure out all the edge cases. Because if you don't figure out one of those edge cases that comes up, you got a problem as an engineer. And so this is a totally different way of doing it. You give it a whole bunch of samples, and we'll talk about that, but we're not explicitly trying to find those edge cases anymore. We're letting that happen through training. So we're going to gather the knowledge from that training and without specifying it explicitly. So fundamentally, deep learning is modern deep neural networks. It is one. If you say deep neural networks or even just neural networks by today's standards, because honestly, except for toy examples, there's no such thing as a non-deep neural network anymore. So deep learning is kind of the field, and neural networks are what you do in the field. And this is kind of how it fits in. Deep learning is a part of machine learning, which is a part of artificial intelligence, but it's the one that's getting all the hype and the news. And in a larger sense, just kind of putting it in, you can't have deep learning without the context of big data, because you have to have a whole bunch of training, which we'll talk about that. And there's a lot of data science that goes into the models and such like that. So a really fundamentally important thing is a lot of people that aren't getting into deep learning kind of think of it as it's a field in data science. And I would argue that. I think it is partly a field of data science, but it's really this juxtaposition of all these different things that come together. And if you put them all together and you have your software engineers and your data scientists and everything, you can get there. And we'll talk about the specifics in a few minutes. And this is just a timeline kind of when people were interested in different stuff and how it came about. Different way of looking at the same information. So Obviously, we're seeing huge growth in recent years, and that's basically because we have cloud resources available to us now. We have these huge data sets, and frankly, the algorithms are getting rapidly much more sophisticated that you can apply. We started with backpropagation, in years past. That was around back when my dad was doing it. But there's so many more things that are happening, and it's speeding up. It's just crazy how fast this is moving. As a career technologist and a career engineer, I have never seen any field, and I've moved around in different areas from networking to programming to infrastructure to you name it. I've never seen anything move anywhere close to this fast. So it's just phenomenal. So why does this stuff matter? Well, there's the obvious things. We see self-driving cars. These are the Google cars. Everyone's talking about bots, chat bots. It was a problem. One of the things when I was at Accenture that just annoyed the crap out of me, pardon my language, is that we were talking about selling bots to customers, and I'm like, that is just the tip of the iceberg. That is the easy stuff in this field. There are so many things you can do way past that, and the potential of the technology is pretty remarkable, so long as you set your expectations, down to earth on what they could do. So these are common use cases, and it's kind of by field. Basically, you have security, you have marketing, you have machine vision, you have different types of natural language processing, speech recognition, self-driving cars and transportation. We're coming up with trucks soon and other things. Healthcare and finance. And these are just barely touching, barely touching the surface on that. So this is nowhere close to being a comprehensive list. And this is something, I just added this last night. Andrew Ngee, I always am not sure I ever get the name right. But he was talking about with today, you have an input, you get a response, and what kind of application is it? It was just a very pragmatic way of looking at it at a basic level. And so I threw that in literally last night, just for another perspective on how you might think of these technologies in a real day-to-day sense. So this deep neural networks can precisely approximate any continuous function. That is a boring statement if you're not a mathematician. I just got to say, just horrendously. But, if you really think about it, what it's really saying is if input, then output. And nearly any process imaginable involves computing a function. If you start your coffee maker in your kitchen in the morning, there's a process, there's a function that's happening there. When you start your car, there is. It's really, really hard to find something in your life that doesn't really, when you boil it down to its concepts and what's happening, that are a bunch of functions that are happening in order. And that's a pretty powerful statement. That is huge. It basically is saying that neural networks, that the field of deep learning is universal. And that's not something that any other technology that I'm aware of has ever been able to make a statement about. And that's simply because you can approximate any continuous function. So I see a lot of talks and read a lot of stuff on neural networks, but I rarely see people draw out the why. And people will leave and they'll be like, it's this great thing, but why? What is it? What is the magic here? The magic is that. That is the magic right there. And then everything else is just how you're implementing that. So it's a universal approach to solving complex problems. The world's first. So a little bit more of the why. You're probably already aware of this. This isn't recent news. Google, they went mobile first for basically the last 10 years. And last year, they decided everything, we're switching off that. Mobile is assumed now. Don't stop talking about mobile. It's not cool to talk about mobile anymore. If you're not mobile, hang your head. At this point, they're going back and they're moving all their services into AI-oriented services. And we'll talk about the specifics of that in just a little while. But they've literally done, over the last year and a half, almost 2 years now, what Honeywell is now doing with me there. And we are going through every product and service we have and figuring out where deep learning applies, which is what part of last night with my CTO was about, much to my dismay. So you will certainly consume, and you'll probably create AI and ML microservices, and probably going forward for the big stuff, most of that's going to be deep learning. And so Dan Ollie isn't, in my view, a particularly well-known guy. I didn't know who he was until I ran across this article, but he has a great point here. And this article is, a year and a half old, I think. April 2000, about a year and a half old. And his point is, if you had invested in this stuff, just a little ways back, you would have spent a ton of money for very little return. And if you wait till we get just a little farther down this timeline, you're going to be hopelessly behind. And so I don't know if his year projections or where we are, I don't know if he's exactly right on that, but his underlying point is spot on, is that we're at that moment right now where the cost curve has dropped dramatically in terms of being able to get into this technology. And if you wait at this point, your competitors are already surging ahead. And this is that moment where you want to invest. And that statement holds equally true for that 3-person startup as well as the Honeywells of the world. It doesn't matter which thing, because the cost is so low, you want to get ahead of that market. This guy, who's not one of my favorite people in the world, I'm biased there, has figured it out. And he's basically, this was September 1st, and he was telling a bunch of computer science people at a Moscow university, get on AI, because that's what we have to do to get where we want to go. And there are great people in the world with great ideas toward this technology, and there are people that may be a little bit more self-motivated on what they want to do. But it's coming. It's coming because everybody's doing it at this point. Sorry, I had to throw that in there. I felt the need, so just couldn't help it. So there's a couple of moments here where, because it's important on getting the idea, I want to throw out some things. There's a textbook here, and I'm going to reference it. Some of you who do this may already know it, and I'll talk about it later, but there's some key concepts in there. And deep learning is a hierarchy of concepts that enable the computer to learn complicated concepts by building them out of simpler ones. And we're going to look at that in a very pragmatic way in a few minutes. So you draw a graph showing how these concepts are built on top of each other, and the graph is deep with many layers. And that sounds really like, what the heck? But we're actually going to show this in just a few minutes. So how does deep learning work? We're going to have some fun with it. Training enables generalized predictions using known correct results. This is a particular type of deep learning, in this case called supervised training, which most of you are familiar with. It's the dominant thing right now. There's a lot of unsupervised work going on in research. But this is, if you're at a Honeywell right now and you're doing some research and doing a whole lot of implementation, this is kind of where your bread and butter is. That will evolve over time. You got to have lots of known correct results. And when I say lots, a very trivial application might have a toy application. It's not meant for real life. It might have like 10,000 things going into it. A real small thing might have 100,000, and then big stuff, maybe 10 million is not uncommon. So we'll talk about that on delivery, because there's a huge implication there that I'm going to circle back to in just a little bit. So once you're trained, you're making generalized predictions from new results. In other words, I've just done a training set with 10 million things in it. And there's going to be a use case comes up, which is that 10 millionth in one use case that's never been seen before. And your well-trained network can actually figure out what that is, and the one after that, and the one after that, and the one after that, because it has generalized knowledge. It hasn't memorized the data set. So you're allowing computers to learn from experience and to understand the world in terms of a hierarchy of concepts. And each concept is defined in relation to simpler ones. And that statement is very pragmatic when we look at the architecture of what a neural network is, which we've just arrived at. I told you I moved the slides around, so every time I hit the forward button, I'm not quite sure what I'm going to get next. I talk about this all the time, but the order changes slightly every time. So we're going to take just a moment and race through this really fast. And so I have a tiny neural network. Theoretically, it's deep because it has more than one hidden layer, which we'll talk about that. We have an input layer, a hidden layer, a hidden layer, a hidden layer, and an output layer. But in real life, this is even smaller than toys. This is for demo. This is just for discussing the idea. And you have an input, and you have something in here that's called an activation function, or arguably a transfer function, and some people would say that you could divide those things up. It kind of depends on which book you're reading and who you're talking to, but fundamentally, there's a fairly simple function. We'll talk about that. And you basically, and this is the most basic type of network that we're talking about. It's a feed-forward network, which means Everything is going that way together. And we're talking about a concept to train this called backpropagation, which is the granddaddy of the types of algorithms that you would train a neural network with. And there's lots of other options that are not this, but this is the one that everyone learns in the very beginning. And so as you come through here, you have a bunch of inputs. They're all numbers. Whatever it is in this continuous function, we're going to go model self-driving cars. And you have to break down all the data into numerical values. It only works with numerical values. And you drive each of those in as features in data science speak into the inputs, and you drive those across your various nodes. In the beginning, all those arrows that are there have randomly chosen weights. It's an untrained network. And so you push all that through. Remember, we're doing supervised training, which means, and maybe I should explain what that means. I have a data set for training, and I know what my reality is. It's labeled. For everything that has gone through on that, I've gone and I've actually said, this is good, this is bad, and I know what those outputs should be for the purposes of training. So I know what my real output should be. And on that first iteration through, I'm nowhere near that. And so I'm looking at that output, and before I go into the reverse, I want to show you what the inside of each of those nodes is going to be. You have each of those inputs that goes into that transfer function that we talked about, and potentially into an activation function, depending on how you look at that, separate it out. And basically, that transfer/activation capability is providing the nonlinearity that you need out of each node. So this is why you're able to get these wildly complicated problems that you're trying to solve. And if you have 5,000 layers on a big problem, and each of those layers has, let's just say 5,000 nodes across. It could vary layer by layer, but that's quite a lot of nodes, and they're all fully connected like what we showed on that last one. And each one of these neurons is going to take whatever values, the sum of the values that reaches that neuron, run it through the activation function that you've chosen, and then output that and combine that. So it's really, really computationally intense. Thus the supercomputers we were talking about earlier. So you're updating each of the weights in the network so that they cause the actual output to be closer to the target output, minimizing the error for each output for the network as a whole. And the way that's done is you take that, and I said, remember, we're way off from what we know to be the truth as we're training this. So we push it back through, all the way back through there, and we are adjusting the weights and calculating the error. And basically, you're taking derivatives on the way back through, on the back side, to figure out, well, this is where I want to be, and this is where I'm at, and how far away am I? What's the slope of that? You know, do I want to make a big jump to try to get there? Do I make a little jump when I do error correction? And every single node has to do that within the network. And so you push it all back and you adjust all the things and you get back to the front end and you've done one iteration of training. Remember, that's one row of data that you've done. We're going to do 10 million minus 1 going forward. So we have a lot of computation in front of us, and hopefully over time that error gets reduced and reduced and reduced and reduced. So basically training is a search. It is a search algorithm. You're searching for the set of weights that cause the neural network to have the lowest global error. And when you get to what that error is, at some point you get within a measurement. You say, I want to be, I'm just making numbers up, 95% accurate. I want to be 99% accurate. I want to be 99.99999. Well, there's a cost to that level of accuracy, to that reduction of error rate, and you keep running these until you get there. And if you get to a point where you're now within that, you stop it because, hey, you've just gotten to where you want to be. That network is sufficient. And if it's a fairly trivial thing that you're building it for, in terms of, if it gets it wrong from time to time, it's not that big a deal. Maybe 95, 96, 97, 98% is okay. For a lot of really crucial things, you're in the nines. But the farther you go on that accuracy curve, that's a lot more training that you're doing. And at the end, you have a trained neural network that kind of looks like this. If you're talking about those weights having been adjusted, every single arrow has a unique value in it. And that becomes locked. I got there, I got within my parameters, and I've locked it in. And at that point, I have a neural network. Then I can go out and stick it in something that I make at Honeywell. And it's now a component piece of software inside that. And now I can shove data through that model, which is locked down on those values, and it should give me an inference on the back side that is pretty darn accurate, at least based on what I've asked it to do. And that is fundamentally, in non-technical speak, how a neural network works. And this is the heart of AI today, whether it's self-driving cars or anything else. There's a lot of variations and there's a lot of build upon this kind of things, but that's the core concept right there. So deep learning is very flexible because it represents the world as a nested hierarchy of concepts, and each concept is defined in relation to the simpler concepts. So each of those layers, and I'm going to give you a little bit of a wishy-washy answer, each of those layers is aggregating those concepts. And so you get something like, if we were talking about vision, you might be starting to say, oh, I recognize a difference in a gradient between a light area and a dark area. And then the next, as you move down through that and go through some of the processing that a convolutional network, which we'll talk about in a minute, does, it goes, oh, that's a line right there. And then the next one goes, oh, that's an edge, actually, to an object that's a larger thing. And you start building these out. So when we're doing this really complicated language about concepts built upon a hierarchy of simpler concepts, that's what it's getting at. It's literally building it up as you go through the network into something that means something to you or your business. So these are common. There's a lot more architectures in this. People always go, why didn't you throw in recursive or one of the others? There's a brand new thing that's really hot called capsule networks. Why didn't you put that in? Well, it's because no one's using it in real life yet. It's a hot research topic. But these are kind of the cores. We talked about feed forward with backprop. That's kind of the granddaddy of them all. Convolutional is fundamentally the machine vision approach for today. And this is evolving very, very rapidly, so it may not be, it has been for a little while, it may not be the primary thing going forward if capsule nets sweep the world up in that way. Recurrent networks, there's lots of types of recurrent networks. A lot of people, kind of the big one for a while was called LSTM, which is long short-term memory, but there's a whole bunch of research in this area and a lot of little variations. So that you would typically find, basically a recurrent gives you the sense of circling back on itself with values, so you have a sense of sequence or time that you can say. So if you're doing speech recognition, recurrent would be really common because as I say this sentence to you, those words have meaning in the context of the order, and I want to know what I just said so that I can develop the context for the next thing. Whereas a convolutional network with machine learning is basically saying, its approach at a high level is saying, I have a bunch of geographic areas, and in most cases they're pixels for us in real life. So chances are a given pixel has a relationship with the pixels around it. Because think, at the end of the day, it's a picture of an object, and there is order in that object. We're not just a bunch of white dots like TV fuzz, when the TV is going shh, like that. So there's a relationship between pixels. And what it does is it kind of cheats. It's fundamentally a feed-forward network, but it kind of cheats, and it says, I'm going to go identify what those relationships in those geographic areas are, and I'm going to simplify those for purposes of processing so that I can get to the end result. What is this thing that I'm trying to identify much faster than I otherwise would? And then finally, the generative adversarial networks is another hot topic, and there's a lot of different use cases, but it's basically where you can set two neural networks to fight it out. That's where the adversarial comes from. You have one that is just generating results from data and one that is discriminating on those results. And it can create things, often like one very common approach is you can take, if you don't have enough data, you don't have the 10 million you need, which is, by the way, really, 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 really common, which we're going to talk about in a few minutes, then maybe you can take a smaller data set and kind of generate valid fake data from which to train the neural network with. There's applications in security, there's tons of different things. So that's another, if you're interested in this, that's another hot topic to follow. And this is a common graph. A lot of the things in here I've stolen off the internet, and the way I attribute is I tell you where you can go to find it, and that way you'll know everything about who it is. So you can always grab the link. And so convolution, I mentioned earlier about the simplifying. So you kind of have an input. A convolution is that region. They're kind of basically taking a region, and you see the pooling thing, where it basically says, oh, there's a relationship here. I'm going to pull these values down. So instead of a bunch of values I have to calculate, I now have a smaller number of values I have to calculate, because there's still a lot of values. If you think about, just as an aside, if you think about just having like 64 pixels by 64 pixels, which is tiny, 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 and that's an RGB number right there, and you're doing at least 64 by 64 on the R, the G, and the B, and that comes out to, I think, something like 10,000 or something, whatever, in that realm. So you rapidly can take a very small image and have a whole ton of feature inputs to get that in. So if it's a big picture, that becomes just prohibitively expensive unless you have a cheating mechanism, which convolutions give you. So you're kind of pushing it all through, and quite honestly, after those initial convolutions, that should look kind of similar to those other graphs I showed you earlier. I said it was a type of feed-forward network with a convolution. And that's basically what that is you're talking about fully connected back there. So fundamentally, that is the state of the art today, but that may change in the near future. So we're finally to the topic that I promised you here. And I basically am going to approach this by talking about some architecture and some of the challenges that we found at Honeywell and that we know that other people are dealing with as well. So this part right here is about deep learning and you. This is the reality after we've done the training. And I threw this in just for fun. Well, yes, of course we do AI. It's, everybody, surely this Christmas season, as we go into the holiday season, have you noticed that every product under the sun is claiming to have AI in it? Has anyone noticed that? I heard a data scientist that I follow mention, basically, if there's anything that you're doing with big data at all, whether it's deep learning or not, people are just kind of putting that AI tag on it, which is probably pretty accurate. And maybe in some cases not big data. So deep learning automation is expensive to implement and scale. There's a lot of different ways we can do that, and we can discuss, and we can also stop, and I can take questions. Everyone's been really quiet. Before I move into this, does anybody have any burning questions they want to ask right now?
So you keep referencing this like 10 million data set. Is that a factor of cost to opportunity, or is it a mathematical?
It's a rule of thumb. So that's a great question that you're asking. So right now, this is just me saying this. We're in the Wild West days of deep learning. So, and I'm getting to an answer on why I'm going to say this. Right now, if you like when the advent of the internet. This is about 1993 with the internet and the web just coming out and everything. We're in the equivalent. So this is 1993 for the internet coming out for deep learning. So if you actually, suddenly in the last year, there's tons of books coming out and everything, but I don't think I've seen yet a deep learning best practices thing. So it's kind of a rule of thumb that people talk about for the size of the projects, and it might be a starting point, might not be the right one. But people kind of say, this is the complexity of what I'm trying to deal with, this is where I'm trying to go with it, and based on things I've seen, I'm looking, it feels like 1 million, feels like 10 million kind of thing. And you start and you learn from your mistakes as you go and you move on. But I don't think I've seen anything that's a mathematical proof that says 10 million for X thing. So there's a lot of this going on right now. Yeah. So, okay. If you are doing a fairly small, if you are a Georgia Tech student, maybe a Georgia Tech grad student, and your thing is data science, and specifically you're into deep learning and you're doing some projects, you're probably able to go and pick something that's good enough for what you're moving toward, but it's reasonable in size and scope to get it done in a certain amount of time. But in real life, I'm going to go off on a tiny little tangent real quick. In real life, when you get out of that environment and you're in business, everything is driven by profit motive. So, no surprise there. And so you have to find a way to, if you're going to invest in this technology up front, then you have to have enough compute capacity to do that. And make it across the projects. And there's a point where it's not necessarily worth it to invest much for just one thing. It's one thing if it's Apple iPhone or something, and it's a gigantic product. But most of us don't have these completely, sweeping the world. Every time you come out with it, everybody in the globe goes and buys it. It's usually something a little bit less ambitious. But you want to invest in AI. So to do that, you've got to not only create the capability, but be able to do it across product lines and stuff. And I'll talk about that in a little bit more detail as well and how we're doing that. But that means that compute power rapidly can go from I have a small GPU instance in AWS that I'm using to do training to like hundreds of those if that's what you're using, and or even thousands you can get up into. And that so you get to a point where you kick off the cost curve and it goes flying. I mean, really, really high. And so like for us, at the scale that we're wanting to do it, where we're going through different product lines and we're going, I have a printer there, I have a scanner there, I have a robot here, I have a speech recognition headset right there, and we're having to analyze these things. You get to a point where the cost of cloud computing actually gets better to buy a supercomputer to do that. And so you have to kind of figure out where you're at, where on that scale curve you want to play, and how do you get there without breaking your company. And that's a really, really hard thing, to be perfectly honest. I told you, I told you I had a presentation in front of my CEO about a week and a half ago. It's on a Sunday. He called us into the office on a Sunday. So my wife wasn't happy with that. And we're talking about the supercomputer, and he's like, well, how many are you going to buy? And I'm like, no one's ever asked me how many supercomputers I'm going to buy before, you know? I come from small companies and startups and all, and, you know, first of all, the idea of supercomputers are just like, you know, really? Sure. And then, you know, he's like, well, how many are we going to go? How far are we scaling and all that? And it was, and that was where, even though I'm already in the job and in the position with the decisions, I was like, whoa, that totally blew my mind that I would be asked that. So, hey, I've gone off and I'm just planning forward and, you know, figuring out what that's going to be for us. So this, you know, basically leads into, it's a strategic investment from leadership. At whatever scale you're going to be at, whether you're a tiny little startup and getting ahead of your competition, doing the innovative thing that you're thinking that nobody out there has done, and you're 3 people or 10 people or 20 people, you know, that is still an investment with those limited resources you have. You have to decide how important it is and how big a taste you want to get. And for us at Honeywell, it's, you know, it's how many millions of dollars are we investing in this stuff? And, you know, and literally, you know, that supercomputer conversation, he literally said, I forget what the exact question was, but he said, I'd like to know the answer to this, blah, 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 blah. And he said, and by the way, your answer is going to decide on how many millions I'm spending on this or that. And I'm like, I hadn't even thought about it, you know, up to that point. And it was just like, but he is afraid if he doesn't do it at his level, one of the competitors, you know, maybe GE or somebody like that is going to come out and do it before we get to it. So it's whether you're huge or whether you're tiny, it's still driving that. So, and I mentioned this earlier, I want to talk about talent a little bit. This is a really common misconception. Everyone thinks that deep learning is just, hey, it's data scientists. Take our data scientists and throw them at deep learning. And I got to tell you, I came into Honeywell and I have a different perspective because I told you I'm a software engineer by background. But I inherited a whole bunch of data scientists, and I said, hey guys, we're going to go deep learning, okay? And they all went, we haven't done that. No, we've done other things. We've done a little bit of machine learning and stuff, but you know, this is the Wild West days, and just because you're a data scientist doesn't mean. So we got into training, and so for us to be a data scientist at Honeywell, at least within our division of Honeywell, it means that you have to be an AI person too. It's no longer sufficient for me as a hiring authority for you to come in having graduated with a master's in data science. If you haven't done deep learning and gotten experience and understand so you can jump into the team and start contributing, then that's not going to help me. And so I talk about this a lot. I do need data scientists, but I need those that know that. I need amazing software engineers because we're a manufacturing company. And so at the end of the day, it is not an insight that we're turning out. We don't, it's the beautiful visualization for the CEO, that's not what we're doing. We do that, but that's like, oh, okay, the CEO's asking, he gets the least capable person to do what he's asking for. And we keep the AI-oriented people, so at the end of the day, it's going to become a component. It might be a Docker container that's wrapping a model, a deep learning model that we've trained on that, and that we're sticking out into a product, or in the cloud to support a product, or whatever, wherever that happens to be going. So it requires all these things. There's a lot of disciplines that go into successful deep learning. I just got back from Pittsburgh, so I know a little something about deep learning. There are people that know a lot more than I do. There are people that know less than I do. But, you know, I got up there, and these guys in my Pittsburgh team are experts in speech recognition, natural language processing. There's so much domain expertise there that every time I'm there talking to them, I am like a student again. I'm like a freshman walking into class. And I may know deep learning and understand the underlying technology they're using, but the domain knowledge is huge. And there's so many spaces. If you're doing self-driving cars or whatever, there's just enormous amounts of domain knowledge that need to follow in. So just going out and getting a deep learning capability will not get you there. You've got to have people who understand the specifics of what you're dealing with. I love it because right now for this little moment, I get to be the guy who's doing the teaching. But yesterday and the day before and the day before that, I was like, really? How'd you do that? Wow, that's so cool. And so that's this field right now. Boy, it's moving fast too. So you recruit the best people you can find. And I mentioned Andrew Ngui later. If that's the last name, I never had. Someday I'll figure out if I'm right on the pronunciation. But he was saying something in a recent article. He was talking about the AI wars, I think it was. And what he meant was the hiring is that there's so few people, even within the data science community, there's so few people who really understand how to use the technology that, yeah.
How is NLP and speech used in real life?
Let me swing back. I'll be happy to answer that, but let me swing back. There's a moment where I'll talk very specifically about some of the choices we've made, and I'll address that then. And if I don't, raise your hand and do that. So you really, that's what I'm searching for. I probably can't afford the world's best people because I work for a corporation, and they don't always pay the very best. They pay okay. They don't pay, but if there may be teams out there that can do better. It's something that I'm constantly going back to our finance function and saying, give me more, give me more. We need to be able to do this. But you get the best people you possibly can. And whatever you get in the door, you train them like crazy. And that's just the real life because we're in the Wild West. And there just aren't enough people out there that are doing this kind of work. So one does not simply do it. There is data that does not stop. So an executable AI strategy requires a prerequisite, and this is really, really, really important. Prerequisite and fully executed data strategy in place ahead of time. So when they hired me into Honeywell, boy, I hope my CTO doesn't see this because I'm going to say something. He said, I had to interview with him, and he said, we got tons of data. We got data everywhere. It's true. We have so much data. Big data galore. But it wasn't the right kind of data for me to train the specific use cases that I needed in the neural networks they want. We hadn't gotten the data we wanted from the things and all that. So a big part of what we do is work with our product development teams to say, to get your product better, we have agreed in our collaboration that you want to do this. And if you can do that, you're going to knock it out of the ballpark. And I said, to do that, I need every bit of data relevant to that problem that you can possibly give me. And I need a lot of it. And they go, okay, we got log files. We got maintenance files. And if you think for a minute, you got log files, and what they want to do is they have a robot, maybe, and you want to do speech, computer vision to identify things. And you're like, log files aren't going to get me there because log files don't give me what I need to train 10 million lines of data so that I recognize that this is a thing that I care about from the convolutional neural network. Saying that it broke at 10:38 last night doesn't help, no matter how many of those you did. So you're going to have to organize this. If you really get serious about getting into AI, do this first before you ever talk about AI. Get your data in your company flowing. Figure out what matters for your products and drive that to the place where you're going to do the training. These days, that's getting really complicated because the last few years, trainings had to happen in the cloud or in a supercomputer that's at a centralized location. But we're now getting the capability, Qualcomm Snapdragon, if anyone knows what that is, we're getting capability for doing networks on edge devices, for doing training, ongoing training. You can deploy something and continue to train. So you have to get data from those devices in, and then you have to circulate it back to where you need it for training. And that is a really, really, really complicated thing to do. And literally at Honeywell, we have hundreds of people working on just that. Nothing but that, because it's that big a deal. It's bigger than the AI issue itself in terms of training in a lot of ways. And that was my gratuitous data. Oh my God, we don't have data everywhere. And so here's some questions we have to start with. What problem are we trying to solve? What data do we need to solve the problem? What data do we have? Where's it coming from? How will it get to us? Do we have enough of the right data to train the models? Where will that data be aggregated and maintained? What pre-processing and post-processing is necessary for that data to be useful to us? And what enterprise and data architectures will be used? And if you can't have that sorted, what's on that sheet ahead of time, just like done. And by the way, you can take pictures, that's no problem, but I will also post this online. And I haven't yet, but I will do it, and I'll real quick figure out at the very end. I'll give you a URL or throw it up that you can find it at. So have all that sorted before you ever talk about AI, before you ever get to deep learning. These are a bunch of the most popular frameworks that are out these days. There is not necessarily, this is one of those religious topics where you can bike shed, meaning that you can argue my favorite versus your favorite and everything. They're all really fabulous. Some have strengths and weaknesses on others and stuff. Right now, some of the biggest ones, with Caffe and Microsoft CNTK and MXNet, which Amazon uses, it's open source, but Amazon uses it, and TensorFlow from Google. And so you have to pick what you think is the way to go. And actually, before I go on, TensorFlow right now is the biggest in terms of market share. That doesn't mean it's the best, but it's gained because it's Google. It was released a couple of years ago on November 9th, if I have my date right. And that's what really shook the world, because you had these other frameworks that were already out there with people interested in using them and all that, but nobody had mind share in the market in terms of really owning the space. And because Google said, hey, by the way, all those services you really like to use that we offer you, many of which are free or whatever, this is what we drive that with. TensorFlow is integrated into every one of those Google services that you use every day. And so, the spam in your Gmail and the Google searches and all the various things they do, all the subtle things, it's all driven by TensorFlow. And because that's pretty much as battle hardened as you can possibly get for a framework, people are like, well, it's Google. It's kind of, for those of you who are closer to my age or even older than me, you may remember back when IBM was the thing. If it's IBM, that's the choice. You'll never get fired for choosing IBM. Hey, IBM PC, well, TensorFlow in this day and age, it's that you can't get fired for using Google. It's kind of how people tend to look at it. And that's one of the reasons. I'm not saying it's the best, but it has the biggest mind share right now. You can do it on all these platforms. And at Honeywell, we use all of these platforms plus our own data centers with supercomputers in them. So anytime one gets a head start, the others tend to catch up. There's some small differences in them, but depending on how you're approaching it, whether you want managed services, there's all these AI managed services that they're all putting out, or whether or not you want containers or just spinning up instances and doing it, you have to watch it month by month to see who's doing what.
Any current situation about which one is ahead in what aspect?
I have biases there, but I'll share those biases if you want.
Yeah, and also for the previous slide too. I know, for example, MXNet is slightly more performant than TensorFlow. Similar, if you have similar knowledge to share. Yeah,
I do. Right now so Honeywell as an organization, beyond just my function, is using tons of Azure, which I'm not the biggest fan of. It's number 3 in that list for me. And for AI, we're getting more and more into Google Platform. I'm actually, it's not strictly my choice is the problem. I'm actually an AWS, I'm a solution architect with AWS. So I have that, I've done that investment and skill, and I actually just let my certification lapse because I don't really need it right in the position I'm in right now, but that's where I've had all my time. So when I go do something by myself and I'm not using the supercomputer, I usually spin up an AWS instance, even though that's not official Honeywell. They'd say, "Don't do that, Chris," and I'd go, "Okay," and then I'd go do it. So I want to talk a little bit about our choices, and this come back, and you can ask me your question in a second. I actually forget what it was right off that, but all these things about what we're doing. I'll address. So I want to kind of talk about how we see ourselves and what we do. And this is not meant to be, by the way, a commercial for Honeywell. What I'm trying to do here is we've gone through this process. I'm not trying to sell you on anything. I'm trying to give you some insight into how we approach extracting a value here. And so this actually didn't exist before a week and a half ago. I put this together for my CEO so he'd understand our AI group in this. So this is a brand new thing for me. So we are trying, and I've told you this, to improve our product capabilities. Because, hey, we're a manufacturing company with some services, and we are all over the globe selling stuff, industrial things and aerospace things. And so for me to be valuable in the company and for AI to be valuable, it has to help our products. And so, and I kind of talked about the second line as well. We want our products not to just be products, but to be smart products, intelligent products. And so that looks a lot, if you think about that, that looks a lot like software development in a loose sense, doesn't it? You know, you're there and you have a continuous integration, continuous deployment for what you're doing in your software world, and you're, you know, creating containers in the modern, you know, in 2017, that's what you do, and pushing those out from a DevOps sense. And that's really what deep learning is. After you've gone through all the modeling and figuring it out and running the data through and training everything, you got a trained model, which is nothing more than a piece of software. And that software gets wrapped in some mechanism to deploy it and pushed out through your CI/CD into products. And that's what we do. When I have a new data scientist that comes into our group, I drill it into them. We don't do insights. We don't do insights. We don't do insights. Or you can, but you're going to be the guy in the closet over there doing insights. This is where we bring huge value to our products. And that's what we're doing. That's what Google is doing. That's what everybody is doing now. That is the only way you can do it going forward and make it worthwhile from a P&L standpoint. Trying to maximize data through AI innovation. So every project is different. Every one of our AI projects, I'm looking at it and I'm saying, either it is an existing product that we're trying to enhance, or there's this whole new idea for a product. And what are the right tools to bring? You know, what makes sense? Because you don't want to shove deep learning into something just for the sake of it. You want to actually, you know, say, hey, there's a value add here, and it's worth that investment of time and effort from the team. And there's also opportunity cost. Whatever you are working on, that means there's other things you're not going to get to work on. So you're making that evaluation. And then we're going back to our product design people and saying, this is pretty cool right here, but if you were to work with this, like on that data stuff I was talking about before, or if you were to add these sensors to this, add these sensors for this new data stream, boy, the things we can do for you then, that's amazing. And so AI feeds right into product development in that sense. And then I told you what my background was. I'm a startup person, and so we make mistakes. We have to make them really fast. We run hard. It's the Wild West of AI. They kind of know that, and so we're trying to iterate as quickly as we can. And then the bottom is just kind of the hoorah part, you know, let's go get them. But that's important, because when people feel they're working on something that's meaningful, it's going to have a big impact in the market and make your job meaningful if you're going to bother to show up for it every day. That's a pretty important deal that you feel that way about it. We've chosen TensorFlow for very pragmatic reasons. I'll correct that. I chose TensorFlow. And I had some people on the team say, but I like Caffe. I like MXNet. And I said, I love you guys, I love you, and guys generically, when I say that, I love everyone, but it's TensorFlow. And there's a really pragmatic reason from a management standpoint. It basically has all the capabilities of some others. You can debate which one's better or worse, but it has huge market share. More people are using TensorFlow than the others. There's probably more people using TensorFlow than all the other frameworks put together right now. I can't substantiate that with data, but that's just the sense I get in the marketplace. And there's a lot of support for it. So if you're looking at trying to hire in a team, I have to bet on something. I have to place a bet and live with it, and that's the IBM right there. And was that anywhere close? I forgot what you asked a little while ago.
Yeah. About voice and NLP, how do you use voice and NLP?
Okay. At the end of this, NLP is in my head. I'm going to finish that. That's specific enough to where I'll grab it in a second. I've already talked about this, and we did that because we crossed that curve where cloud computing wasn't going to be the most cost-efficient way to get where we want to go. It also has processors that are, even the GPUs, by the way, that are in the cloud providers, you get their supercomputer, and it's 2 generations newer than whatever the cloud providers have. So that's why that's what lures NVIDIA customers to actually buy from NVIDIA versus always going to Google or somewhere else. And did that, seem to be going back. We have invested in these things. You've probably heard of the first two, and I'm betting a few people in the room. Anyone ever heard of pachyderm? I'm just curious. Nope? Not a single hand, huh? Ha! Okay. So that's my find. That was my startup find. And I'm not going to try to sell them, but everyone's heard of Docker. Most people have heard of Kubernetes, which is Google's. It's an orchestration system, which if you don't do Docker, it means kind of the way you're managing Docker containers in a loose sense. And that's built into everything we do at Honeywell. Everything was containerized, and that's a very modern. Pachyderm is something I found, which is, does anyone use Git and GitHub? Yeah? Okay, so imagine that you had Git available for data instead of your source code. Imagine that you could branch it off, you could do lots of, trivially, like just as easy as you do it in Git. And you branch off and you run it through, you maybe run some iterations and you get to a point and you say, I'm going to stop it midway through training right there. I'm going to branch it off and I want to try several experiments on this right here. And then I want to roll that back in later on and try something else. All the things that we do when we're slicing and dicing source code and trying different experiments with Git, that's what Pachyderm can do. It's a tiny little startup. So I've never yet had a crowd in front of me that goes, I don't know what that is, but I think there's like 8 people in the company, maybe. So that's what we use to feed our supercomputer. And so the future of deep learning, and this is going back to that Ian Goodfellow on the left, all these guys, really, but Ian Goodfellow is one of the most famous guys in deep learning. He's the guy that invented the generative adversarial networks that I talked about a little while ago. And they're basically just saying, it's the Wild West. We're doing a lot of changes, a lot of advancements going to happen, crazy world. So I want to talk a little about this. Everyone knows how much there is about hype and deep learning in general. So it'll be interesting. This is something Gardner put out in, I think it was July. Yeah, July 2017. Right now, deep learning is right up there, and they have these wonderful names here. Has anyone seen this graph before? They do it for every technology out there. It's not just AI, it's everything. So every single technology comes out and they put it on this graph, and we've been doing the hype curve, the innovation trigger, and right now we're at the peak of inflated expectations, which means deep learning can solve anything in the world. Didn't I tell you that? Continuous function, all that? It can do everything. So obviously, I told you also with that, you have to apply it to the right things and say, I have a particular tool, how do I apply it well? Well, a lot of people are trying to use it for things it's not so good at, or they don't have the right data, and they're not getting the results they want, and we're supposedly about to plunge into the trough of disillusionment, where people say, we wasted $1 million, or a startup, we wasted $50,000, we can't do this anymore, we're going to go out of business. And people are frustrated, but then people kind of get that real, more books come out, more people learn how to do it, and we kind of go up that curve. One different thing I will say about this curve is it may not always be deep learning, but I'm going to abstract it a little into AI. Instead of going out and having your normal lifetime for a particular technology and eventually it gets old and all that, assuming you allow for the evolution of AI technologies, that curve is going to go up for the rest of your lives and probably your children's lives going forward. That curve will change. It may not always be called deep learning, but these AI technology, whatever deep learning evolves into, that is going forward. It will evolve, it will change, but this is a technology that is not going to get outdated. Other than the current version will get outdated, but it will keep evolving and keep evolving. So we live in interesting times. And there's a conversation, I'm doing the closing keynote this evening at 4:30, and it's a fun talk, by the way, but I'm going to talk about that future a little bit. I'm going to throw out some kind of crazy suggestions and encourage the audience to challenge me on it. See what you think. So it's a fun conversation versus this very pragmatic delivering deep learning stuff. This is the book I thought I'd mention. This is the definitive textbook. Once you're into deep learning, it is mathematically rigorous, but it only really covers the basic cases. It actually doesn't cover, it was only came out, I believe, in December of 2016 when it went to print. So it's, a year old now, just a hair under a year old. And it covers the basics kind of that I've talked about here today, mathematically rigorous in its approach. But this is the one there's that everyone references. So that actually, by the way, the image on this, if you'll notice, it's kind of, when you really look at it, if you kind of just look at it barely, it kind of looks like a normal countryside image. But if you look closely, it's pretty freaking weird. And what this is it was an image that was created by one of Ian Goodfellow's generative adversarial networks. And so there's a lot of image generation that happens that way. There's a lot of fun stuff on the internet you can find if you want to play around with it. So if you're serious about this stuff, get that textbook and start going through it. And just final thing, let me check. What time is it? Does anyone know? Am I overtime yet? It's the last thing, but it's about 2 minutes. Okay. So this is something you can find out on the internet. It's on YouTube. And I found a site where I could actually pull it off without it, because I couldn't do that off YouTube. And if somebody knows how to pull videos these days off YouTube, I keep failing at that, so tell me. So this is showing a test that happened about a year and a half ago and was released back early this year. So these F-18s are about to drop something, and it'll zoom in on them. You're going to see these things dropping out. And then it's going to go to a digital grid. And I want to talk you through it. And it's not actually visually very interesting to look at, but what it represents is freaking amazing. And this is the future of warfare. Whether you're the United States, whether you're Russia, whether you're anybody out there in the years ahead. And I'm not saying this is necessarily a good thing, by the way. I'm just saying this is what state-of-the-art in AI is doing in the warfare space. So you'll see little things dropping out on the screen just really fast, little tiny black dots. Those are drones, okay? So it's dropping a whole bunch of drones out there in a test area over the desert. And you have the green things are the physical drones, and the red things are radar. I'm assuming it's radar or some other mechanism. They're dots that are not real, that the Air Force has put out there as targets that are, that the drone thinks it's real, even though it's not a real thing. But the drones are real. And what they're doing here is those drones are self-organizing. There is no human driving any of this. So there are humans that are running these tests on what happens with the red things. And the drones, that whole giant swarm of drones, is self-organizing and going after the targets. And as they change the target configurations that the drones think they're doing, the drones are dynamically changing what they do to attack them. If you notice, they spread out evenly so they can attack everything. They coordinate, so hey, that's your guy, my guy's over here, you go after that one, I go after this one. And as you'll see the red dot, and suddenly the real life drones are flying around the desert, and they think there's these targets, and they go and they go around them. Now they swarm in, it goes to one, and that's a problem. It's on target. So what they do, they circle around it so they have repeated opportunities to go at the target. This is real life, ladies and gentlemen. This has happened in the past. This is old by the US military standards. Those are the actual drones right there, flying around their fictional target. You see the circles there going around that dot? So this is warfare as we all go into the next decade or two. It can happen in an air-to-air scenario, like what this is. It can happen with targets on the ground. It could be for tanks. It could be for an anti-personnel weapon, with small little drones that have weapons attached to them swarming in. So what I'm trying to get at is the stake, and I'm kind of finishing up with this. The stakes on this aren't just Honeywell making products. The stakes on this stuff is huge. It will impact every aspect of your life for the rest of your lives, and your children and your grandchildren and on. And so if there's anything that should make you want to keep track of what's happening in the space, even if it's not your thing, just keep in mind where we're going with this. And this is just the F-18s flying away. So, there we go.